Hello, everyone, and welcome to this episode. A couple of episodes ago, we learned that chemistry has been lying to us for a while, telling us that things are either insoluble or soluble, and that's it. We learned that even things that are actually insoluble are slightly soluble, and it threw all of our lives into chaos, and we've been trying to recover, and it's just been intense. But in an effort to take the next step toward recovery, we're going to take a look at something called the common ion effect, which is kind of a big deal in chemistry. So we're going to start with a similar problem to that episode a couple of episodes ago, and just go with me on this one, and then we'll talk about what the common ion effect is. So let's take a look at this for magnesium fluoride dissolving into water. The KSP for magnesium fluoride is 6.4 times 10 to the minus ninth, not bad. And we're going to calculate the solubility of magnesium fluoride in both pure water, but then also a solution that contains 1.1 molar sodium fluoride. And that may be new to you, so just kind of follow along. We'll see what happens. So let's do the pure water first. Okay. And remember that when it's a solid, we don't know its concentration. And because it's pure water, we're going to start with zero of both of the ions in the solution. This is going to go down by the molar solubility, which is X. This is going to go up by X. And the fluorine is going to go up by 2X. Okay. So again, we have question mark minus X. We have X and 2X. And I started setting up some of these so it take me a little less time. 6.4 times 10 to the minus ninth is equal to X times 2X squared. And I get an X value for the molar solubility of 1.17 times 10 to the minus third. And that would be in moles per liter. That's how many of the compound dissolved. And so that would be equal to the magnesium ion concentration, and double that would be the concentration of the fluoride ions. So that's great. Now let's compare that to what happens when the solution actually contains fluoride ion in it. This is the new wrinkle we're going to add today. So a lot of it's going to look the same. So we're going to have 0 there, minus x, question mark minus x. And this is going to go up by x, and this is going to end up at x. But here's the difference. In this situation, you got to imagine there's already fluorines floating in the solution. So there's actually not a zero starting quantity here. There's actually a zero point 0.1 molar starting quantity for the fluoride ion. That's a big difference. So we're just going to put that in there, and we're going to proceed toward equilibrium. Actually, sorry, should just be plus 2x. And we're going to end with 0.1 plus 2x as our final amount. Okay, so let's plug that in. 6.4 times 10 to the minus ninth equals x times 0.1 plus 2x squared. And I could do the math directly as is, but my spidey sense is tingling here that I could probably do a little bit of a shortcut. And that shortcut is to realize that 0.1 is a big starting concentration compared to what I think x is going to be, because this is actually very, very small. There's more than 3 factors of 10 difference between the KSP and that. And so I'm just going to assume that we're going to say this is approximately zero point 0.1, and we're going to omit that 2x. We're just going to get rid of it. And we're going to end up with something close to 0.1 anyway. So it's a pretty good approximation. And when I do this, I get an x value of 6.4 times 10 to the minus sixth. Okay, and that's the value that I got. Okay, so I just want to double check that. 6.4 minus 9. And nope, I was right. So my spidey sense was tingling that something was wrong there, and it's actually 10 to the minus 7. Sorry about that. But I'm glad we corrected it, so we can all move on and be happy with each other. So here's the deal. When it was in pure water, the molar solubility was only 1.17 times 10 to the minus third. But you start adding some of the fluorines in there, and it becomes something times 10 to the minus 7. That's 4 factors of 10 less soluble than in pure water. And the question becomes, why? Why is it dropping like that? Well, let's take a look at a wording of the common ion effect. Common ion effect is an effect that suppresses the ionization of an electrolyte when another electrolyte, which contains an ion also present in the first electrolyte, i.e. a common ion, is already present in solution. So it's trying to dissolve into a solution that contains some of itself already, and the dissolving of that second electrolyte is reduced. And so you end up with less being dissolved or more being undissolved. So let's take a look at a diagram of my magnesium fluoride situation. So in my magnesium fluoride situation, you got to imagine that there were some magnesiums here in red. There's maybe 4 of them, and I put 8 of the yellow ones floating in solution. And they're having a great old time dissolving and undissolving and stuff like that. If you add some sodium fluoride to it and get those extra fluorides floating around in it, what it does is it causes the magnesium then to undissolve a little bit, because now you've got a higher concentration of the fluorine, and in order to achieve the KSP value, the fluorine went up, so the magnesium has to go down a little bit. It's going to shift back to the left and undissolve some of the magnesium fluoride and try to get back to the equilibrium constant amount. So that's a fun little diagram that I cooked up this morning. So let's do our first pause the video moment, and I'll throw this one out there. Calcium sulfate has a KSP value of 6.1 times 10 to the minus fifth. Calculate the solubility of calcium sulfate in, again, pure water and a solution that contains 0.2 molar calcium chloride. Take a moment, pause the video if you'd like, and come back for the solution. All right, my 2 solutions, I did them on separate slides here. So the first one is in pure water. Similar ice table, we have a KSP of calcium times sulfate, which equals x squared. X was 7.81 times 10 to the minus third moles per liter, and that's in pure water. And then in the next one, we have a situation where the calcium ion concentration is actually starting at 0.2 because of the 0.2 molar calcium ion. And so similar calculation, but now we have 0.2 plus x times x. And I went ahead and made that assumption again because there's 4 factors of 10 difference between those two. And I solved 0.2 times x, got rid of the 0.2, and I end up with 3.1 times 10 to the minus fourth. So we had, again, less being dissolved than it was in pure water. So there you go. All right, so we're going to do one more in a similar manner, and then I'll have one more pause the video moment a little bit later. So let's do aluminum hydroxide. This is a common type of problem that you might see in chemistry textbooks and maybe even on a test somewhere. The KSP for aluminum hydroxide is 2.0 times 10 to the minus 32, which is really tiny. And it's going to dissolve like this to make aluminum and 3 hydroxides. And we could go ahead and start filling in our ice table, question mark minus x, question mark minus x. And we could start with 0 of this, we'll go plus x, and we'll end up with x of aluminum. But here's where things change. And this is something you kind of want to watch out for. There's 2 reasons. There's 2 reasons why the solubility of a substance might be dependent on pH. And one of the reasons is that it has a hydroxide in it. So this is actually hydroxide. Now in pure water, maybe you know this, maybe this is news to you, but pure water already has some hydroxide in it. And we learned this in our acid-base unit or buffer unit. The pH of water is 7. A lot of us know that from middle school or whenever. But it's a pH of 7 because at any given time in pure water even, a small number of water molecules ionize. They're colliding into each other, banging into each other, and trading hydrogens, protons. And so some you actually get protons and some you get OH minus ions. So you get this situation. And it sets up an equilibrium with each other so that 1 times 10 to the minus 7th is the concentration of hydronium or hydrogen and hydroxide at the same time. They balance each other out so it's neutral, but that's the concentration of OH already existing in pure water. And the negative log of the hydrogen ion concentration gives us a pH of 7, which I'm going to add 2 zeros to. So then we go back to our original problem, and knowing that the OH is not going to start at 0, it's actually going to start at 1 times 10 to the minus 7th moles per liter, which is not a lot, but for something like this really ridiculously tiny number, it's going to make a difference. So plus x, and then we're going to end up 1 times 10 to the minus 7th plus x. So again, now we're back on track. We figured all that out. And we're going to put x in there. And we're going to do 1 times 10 to the minus 7th. Sorry, I missed the 3x. So I went back and changed it, though. So plus 3x, and we're going to cube that. Okay. So can I make the assumption here again? Yes, I think I can, because there's, 25 factors of 10 difference between those numbers. I think I'm pretty okay with saying this is going to be approximately equal to x times 1.0 times 10 to the minus 7th. Get rid of the 3x cubed, and I end up with an x value of 2.0 times 10 to the minus 11 as my as my molar solubility. So let's check it out just to make sure. 32. And yes, 2 times 10 to the minus 11 is the molar solubility, moles per liter, which is not a lot. And part of that is hindered by the fact that there's already OHs in the solution itself. So good job on that one. And now we have our final pause the video moment, and we'll do another hydroxide compound. This is mercury 2 hydroxide, and its KSP value is something times 10 to the minus 26. Take a moment, pause the video, show your mastery of solubility, and come back to the solution in just a second. And I'm sure all of you, with your vast display of chemistry skill, ended up with 3 times 10 to the minus 12th moles per liter with a similar fashion. You got to start with that 1 times 10 to the minus 7th moles per liter and work your way through it, similar to what I did. I did make the assumption again. Maybe you're fancier and didn't make the assumption. You might have gotten something slightly different, but we're all friends here. So there you go. A little bit about the common ion effect. It's something you're probably going to see in your chemistry travels. If you have a question you'd like to send to me, feel free to leave it in the comments or send it to me directly. In the meantime, happy solving and have a great day.